The Prolog ISO standard defines many important concepts. Among them, Prolog data is a sequence of read terms, and Prolog text is a sequence of read terms denoting directives and clauses. And because TCGs are now also part of the standard, and grammar rules. So Prolog text is also a sequence of read terms. And a read term is a term followed by an end token. An end token is dot. For example, let's take a simple Prolog program describing a dragon curve with the predicate dragon. When we post the most general query, are there any solutions, then we get answers as expected. And we can use this interaction as a quad, a query using answer description to specify a test and expected answer. And we notice these are all read terms. For instance, this directive is a term with principal functor colon dash and one argument, followed by an end token, a dot. Likewise, this clause, effect in this case, again a read term. The same for this rule, the other type of clause, a term with principal functor colon dash and two arguments. Also this grammar rule, it's a read term, the others too. Also our sample query is a read term, and also the answer and answer description is a read term. So as mentioned, Prolog programs are sequences of read terms, and therefore we can easily read Prolog programs with standard predicates, such as read term and related built-ins. And we can easily analyze and also transform Prolog programs with Prolog. Well, even though we could do this easily with Prolog, we'd like to have a more convenient mechanism for defining transformations of read terms. Such a mechanism is not part of the Prolog standard, at least not yet. However, there are a few commonalities between Prolog systems that help us imagine how such a mechanism could look like. For instance, many Prolog systems, starting with DEC 10 and C Prolog, and including GNU, Sixtus, Scryer, Trailer and so on, provide a predicate expand term relating a term to its expansion. And this predicate is automatically invoked for every term read, leaving the question, how do we define the transformations we want? Well, a very simple mechanism is the extensible predicate term expansion. C Prolog was the first system with this feature, and it's also available, for example, in Scryer and Trailer. And the idea is indeed very simple. We can add in our programs a clause to the predicate term expansion, relating a term to its expansion. For instance, we can say the read term A is transformed, or in this terminology, expanded to B. So in this way, we have extended the predefined expansions that the Prolog system may already provide. And to this program, we also add the fact A, for example. That's a read term, okay? Now, does A hold? No, it yields an existence error. The predicate A is not defined. What about B? Yes, it holds. Why? Well, because of the defined term expansion. We say the term A is expanded or transformed or rewritten to B. It's as if, instead of A, we had written B here. And Prolog systems differ already here. For instance, in GNU Prolog, this used to work with restrictions. When we use expand term to ask, what is the expansion of A, then we get B. But at least before the upcoming next release of GNU Prolog, when we ask, does B hold, then we get an existence error. So GNU Prolog does not take the defined expansion into account for the program, but it does so when calling expand term explicitly. And this is understandable when we consider how the GNU Prolog compiler works, because the expansions are stated as Prolog clauses, and therefore performing an expansion requires a working Prolog system at compilation time. This is not compatible with the architecture of all Prolog systems, and this could be seen as a design shortcoming of this mechanism. It works only if the compiler can interpret defined expansions, so it can somehow access a Prolog system, and in addition to that, the compiler must be able to take clauses into account immediately after reading them, because we expect the defined expansion to affect every following read term. And in fact, only following read terms, and not those that textually precede it. Then what if there is another expansion, say B is expanded to C. And we ask, does C hold? Yes, because Scryer-Prolog expands terms until a fixed point is reached. That is, no more expansions apply. In the case of this program, the fact A is expanded to B, and then B is expanded to C. For comparison, when we ask GNU-Prolog what is the expansion of A, it's B, at least currently. So at least at the moment, systems disagree also in this specific aspect. Should terms be expanded only once, as in GNU-Prolog, or until a fixed point is reached, as in Scryer and Trailer? What can we say about the mechanism? Well, I think it's uncontroversial to say for every instantiated read term, expand term calls term expansion. And term expansion relates a term T to its expansion E. If the call succeeds, expand term uses the expansion E instead of the original term T. And importantly, a term can also expand into several terms, because if E is a list, then all elements in the list are used instead of the original term. And if the call fails, then the original term T is used. Leaving the question from before, is the expanded term also subject to term expansion? Yes, in Scryer, Trailer and so on, but not, for example, in GNU-Prolog. So this is term expansion. And this mechanism is quite expressive. We can use it, for example, to implement DCGs. For instance, let's consider the Dragon Curve program again, and specifically the first grammar rule here. What does it mean when this read term occurs in Prolog text? What is its expansion, E? We need to use round brackets here due to the operator priority. In Scryer-Prolog, this is the expansion. A Prolog term with principal functor :dash and 2 arguments. In other words, the grammar rule is expanded to a Prolog rule. Why? Well, let's look at the DCGs library. This library contains term expansion rules, and it defines them in the scope of the module user. And they therefore apply not only locally here in the DCGs module, but for all programs that use the library. So this mechanism, term expansion, is expressive enough to implement DCGs. That's not the only way to implement DCGs, but it's quite convenient. And this was also one of the first motivations for such a mechanism. And it can do much more. We can implement arbitrarily extensive code rewriting also beyond DCGs for any Prolog code. For instance, tabling SLG resolution can also be implemented with term expansion, among other mechanisms. Again, with rules defined in the user module. And here we see an expansion rule for a directive, the table directive. The other rule is for other types of clauses, and it performs quite extensive renaming of goals. See the source code for more information. So tabling is an example for this. And using term expansion, we can not only rewrite existing code, but also generate completely new code. We see an example of this in the CLBZ library. At the end of the file, we see 3 term expansion rules. For instance, there's one for the fact make pass CLBZ, and such a fact appears here. So this fact is subject to term expansion. And what is its expansion? It's this, a list of clauses. So it's as if, instead of the fact, these clauses appeared here in the file. And in the case of CLBZ, these clauses are generated from more declarative descriptions. So this is an example of using term expansion to generate new code. One could say a really extensive rewriting of a single fact. And just to give another example of this, the implementation of attributed variables also uses term expansion. In this case, again a directive is expanded, like in the table example, but now it's the attribute directive. This expansion rule uses Prolog load context to determine which module is currently being compiled, so where the expansion is taking place. And in the case of attributed variables, the module is important because the expansion generates code where the module plays a role. Here's a sample query that you can try using the CLBZ module as load context. And here's the generated code in abbreviated form. It's again a list of clauses. Another and related use case is code augmentation. For instance, we may want to add certain clauses to all programs that use a library. And a Prolog system may provide this feature with the virtual read term end of file, which gets a chance for expansion at the end of every file. May provide this feature. Currently, some systems do and some don't. So a common standard would be nice. And of course, countless other examples. For instance, the upcoming package manager package expands use module directives to enable the loading of packages. And it rewrites such directives to ordinary use module directives where the package is mapped to a local file name that is described here. So already such a simple term expansion mechanism is very versatile. Nevertheless, it's only the starting point for these considerations. This is one of the simplest mechanisms we could come up with. It's great that someone has thought of it, no doubt, and we can use it to implement many interesting use cases. But we need something better. For instance, Sixus Prolog already provides a significant generalization, term expansion with 6 arguments instead of 2. The additional arguments are used to provide more control over the applied expansions and to let us reason about relations between layout texts for source-linked debugging. Further, Sixus Prolog invokes term expansion also for queries, that is, for read terms with principal functor !dash and arity 1. And in addition to end of file, Sixtus also expands the virtual clause beginning of file. These are all very sensible features, right? However, is there something even better? And let's think about it. What else do we need or want? For instance, what about quads? They need more than this. Why? Well, consider this query. It contains a variable, these in this case, and in the answer description, this these also occurs. So the query, a read term, is related to the following read term via shared variable names. And an ideal expansion mechanism would maybe be expressive enough to implement even quads. So please help find such a mechanism. Now, let's consider a very specific case of transformations, changing a goal everywhere it occurs. And of course, we can express this with term expansion, right? We could define a rule for term expansion where we say every rule head body 0 that occurs is changed to head and body, subject to certain constraints, namely body is like body 0 except for certain goals which are replaced by others. So we can do this with term expansion, with the clear advantage that we can access the entire rule and therefore all goals in it, even goals that are variables, that is not yet known. So we can detect this and transform such goals in dedicated ways if necessary. And this advantage is in fact also a disadvantage, because operating on the entire rule body is tedious and also error prone. For instance, are we applying the expansion correctly to all goals? Are we taking all possible control constructs into account? And all ways in which the constructs can be nested and so on. Also, not everything is clear. For instance, what about goals in queries? Does term expansion apply to them? Yes, in Sixtus Prolog, but what about other systems? And therefore, for this use case, that is replacing a goal everywhere it occurs, term expansion leaves something to be desired. The issue now is that this can be quite useful. And therefore, several Prolog systems provide a dedicated mechanism specifically for this task. The mechanism is called goal expansion. And a simple form is, again, an extensible predicate, goal expansion with 2 arguments relating a goal to its expansion. This is available in Scryer, Trailer and other systems. Sixtus has a generalization of this, goal expansion with 5 arguments, and before version 4 with 3 arguments. Now, why is this even needed? Why would it ever be necessary to change a goal? Can we not simply define a dedicated predicate and use that in our code? Well, the ability to change a goal via goal expansion can have benefits that go beyond using one predicate instead of another. For instance, most, if not all of the uses I've seen so far aim to improve the performance of programs in ways that would be much harder to achieve manually. An example is inlining of predicate calls. In Scryer and Trailer Prolog, this is used, for example, by the format library. This library exports the predicate format with 2 arguments, and it includes a definition of the predicate which is never used. This is here only so that Scryer doesn't complain about the predicate that is exported but not defined. The, in a sense, true definition of the predicate is elsewhere, namely as a goal expansion rule. This rule states that every goal format with 2 arguments is replaced by a conjunction of 2 goals. The first goal determines the current output stream, and the second goal is format with 3 arguments. That's a version of format where the stream is specified, and the other arguments are the same as before. So when this library is loaded, then all goals calling format 2 are automatically changed or expanded to call format 3. And yes, we could have written a dedicated predicate that does this, but operationally that's not the same, because with this goal expansion we eliminate a predicate call that would otherwise be needed. And it goes even further, because the same idea is also used for format 3. Again, this is only a pro forma definition, which is never actually used. The real definition is again a goal expansion rule. All calls of format 3 are replaced by phrase to stream and flush output. It's module qualified because not all programs import library PO. So using goal expansion, we can reduce the number of predicate calls that occur at runtime, at the cost of making compilation more involved. This is inlining. Instead of calling a predicate, we place its definition directly into the source code. And maybe that's not even a good example of goal expansion, because maybe this specific application should rather have its own dedicated mechanism. In any case, it's something that can be expressed with goal expansion. Another use case is partial evaluation. And we can see many examples of this also in the CLB-Z library. For instance, let's consider this predicate, min factor, and specifically this goal. Which predicate is used here? It's KISS, which is also a local infix operator. KISS is short for compactified is. This is like arithmetic evaluation, is with 2 arguments, except that it works on the topologically compact set comprised of the integers and 2 infinities. And there are many analogous predicates, like KISS greater than, KISS greater equal, and so on. So compactified arithmetic plays an important role in CLB-Z. Now let's think about this goal, and especially about its second argument, this arithmetic expression. It's not fully known, right? Because it contains variables. But it is partially known. We know something about it. For instance, we know that it involves a division and an addition and a subtraction. And we know that the constant 1 is involved, and also where it occurs, at least roughly. Now, partial evaluation means that we make use of information we already have. And that's indeed what goal expansion does in this library. In Scryer Prolog, we can obtain the expansion with the built-in predicate expand goal. This is analogous to expand term. The first argument is a goal. The second argument is a module. In this case, let's say the expansion takes place in CLB-Z, of course, and we ask for the expanded goal G. And since KISS is a local operator, we turn this into functional notation, so that it works also on the top level, that is outside of CLB-Z. And this is the expansion. In other words, goal expansion makes it so that instead of the original KISS goal, now commented out, it's as if this conjunction were written at this place. And one advantage of the original KISS goal is clear immediately. The original goal is easier to read and write. It's shorter, contains fewer variables, uses familiar arithmetic notation, and so on. Now, if the KISS goal is so good, then why does goal expansion change it and turn it into a much less readable conjunction of three goals? Well, the expanded version has a major benefit. It makes better use of information that is present in the source code. We say it's a partially evaluated or a compiled version of the original goal. Let's consider what has happened to the original goal. As mentioned, the original goal uses the predicate kiss. For comparison, in the compiled version, kiss no longer occurs at all. We also say it has been compiled away. And then let's consider this plus sign denoting addition. This is part of the second argument of kiss. It's part of a Prolog term. And what we would justifiably expect from such a goal is that kiss somehow reasons about this expression. For instance, one would suppose that it parses the expression, detects that an addition occurs, interprets the addition by adding the arguments L1 and U2 and so on, and analogously for each of these arithmetic operations. But that's not what happens here. What happened here is that in the expanded version, plus no longer occurs in an argument of any predicate, but rather there is now a goal, kiss plus, with the same arguments as the addition above, L1 and U2. Likewise, for the subtraction, there's a new goal, kiss minus, and also for the division. The expansion has compiled the original expression to a sequence of goals. And a key advantage of the compiled version is that large parts of the expression don't need to be analyzed at runtime, because the expanded code invokes exactly those arithmetic predicates that need to be called, and it calls them with simpler arguments. And the expansion is produced statically, that is from the source code, before we even run any program that uses this predicate. And as a result, we expect the compiled version to run faster, because it avoids the runtime overhead of analyzing the expression. At runtime, it's a sequence of known predicate calls, each of which is very fast, because it doesn't have to consider compound expressions, because those have been compiled away. And indeed, this is measurably faster. It's not a big speed up, but it's nice to have. And goal expansion makes it very easy to implement. And we could push this even further. For instance, the constant 1 could also be compiled away with a specialized version of kiss minus that always subtracts 1. And we see from these examples that large portions of library CLBZ are dynamically generated from declarative descriptions using term and goal expansion. And this is automatically done every time someone loads the library. And the predicates that are used in the generated code, here for example, are often quite simple. And therefore we can more easily move them to Rust or Zig for more speed. But strategically, it's better to keep them in Prolog, to increase the motivation for improving the Prolog system itself. So this is an example of goal expansion within a library. It's a small price we pay at compilation time in the hope that it pays off at runtime, because all these predicates may be invoked many times at runtime. And here are the goal expansion definitions for all these compactified arithmetic predicates, kiss, kiss less than, and so on. They are module local. This is a predicate defined in the CLBZ library, not in user. And therefore, these expansions affect only goals in the library itself. Now, in CLBZ, there's another definition of goal expansion. And this one is defined in the scope of the user module. And therefore, it affects all programs that load this library. For example, let's say we load this library in a Prolog program and we use it in the monotonic execution mode. And we define the predicate nut_sum, defining the sum z of two natural numbers x and y. Okay? Now, let's take a look at the listing of this predicate. We can do this with the format library, and we declare the predicate dynamic to make it public and thus inspectable. And then we ask for the listing. Here it is. Now, let's consider the definitions side by side. On the left is our definition, this is what we wrote, and on the right is the expanded code. This is the result of goal expansion. We see that the first goal is the same in the expansion, up to naming of variables. But the second goal, arithmetic equality, has changed quite substantially. It's expanded to an if-then-else, a huge case distinction. The point of the expansion is to avoid potentially costly constraints, that is CLBZ predicates, and to instead use built-in arithmetic predicates when possible, like here to compute the sum, and here. Is can be directly used if a and b are integers, and c is a variable. And CLBZ does that using goal expansion. This true is a remnant of the expansion, probably due to a condition that was recognized as being true. And it's left here as is, in the hope that the Prolog system itself will compile it away. So in CLBZ, we see goal expansion for partial evaluation within the library and also for automatic generation of tailored code in programs with efficient generated branches that are executed under certain conditions. Another use case of goal expansion is to use a different predicate to benefit from argument indexing. For instance, let's consider a small database of Unicode characters, relating a code point to its name. And as an example, let's ask for the name of a certain code point. This is, of course, instantaneous. This is so fast that the time library reports it as 0 seconds. And it's consistently fast, even if we try it several times. And it's also easy to see why this is so fast, even though this is one of the higher code points, which occurs quite late in the file. Well, it doesn't matter where it appears textually in the file, because Prolog systems tend to implement at least first argument indexing. In this case, it means that they build an index keyed on the code points. And in the call, the code point is instantiated, even ground. And therefore, Prolog very quickly finds the matching clause, using a very fast hash-based lookup in constant bounded time, independent of the size of the database. For comparison, what about the other direction? That is, when we ask, what is the code of the character Purple Heart, the same character as before? Here it is. It's still quite fast, but no longer 0. And consistently greater than 0. Why is this measurably slower than before? We have specified an argument, it's instantiated, again even ground. Well, one key difference is that it's now the second argument of the predicate, not the first. And for example, Scryer Prolog doesn't index on the second argument in this case, only the first. And therefore, to find matching clauses, Scryer now performs a scan of all clauses. That's still quite fast in this case, but it's no longer constant bounded. It now depends on the size of the database. So how can we improve this? Well, one thing we can do is to use term expansion to expand each of these facts, code name, into 2 facts. One, say codename underscore, which has the same arguments, code and name, and another fact, say name code, or analogously name code underscore, which has the same arguments, but the name is now the first argument, okay? This means that each of these facts is expanded into 2 clauses, codename underscore and name code underscore. So this is the resulting expansion. And we see that in the expansion, the clauses of these predicates are discontiguous. They are interleaved, codename underscore, then name code underscore, and so on. And therefore, we add a discontiguous directive. So this is our program so far. And the point of this is that we can now write a version of code name with better indexing. Say code name better indexed. We distinguish 2 cases. If the code is instantiated, then we use codename underscore, knowing that it indexes on the first argument. So we get almost the same high speed as before, except for the additional test and the overhead of an additional predicate call. And otherwise, we use the generated predicate name code underscore. This is also indexed on the first argument. So our intention here is to benefit from indexing if any of the arguments is instantiated. But there's still one problem. The names are strings, so compound terms, and they all have the same principal functor, dot with 2 arguments. And for instance, Prolog doesn't implement deep indexing, at least not yet. And therefore its indexing can't tell these strings apart. Now we can manually work around this problem too. For instance, we can help the system with an atomic hash that we somehow derive from the name, so that we can benefit from indexing. And this may require adjustments, for instance here and also here, which I leave as a challenge. And now, and that's the point of all this, we can add a goal expansion rule to automatically replace calls of code name with code name better indexed. And a key benefit of these expansions is that all application code can stay exactly the same. The database of Unicode characters can stay the same. All clauses of code name are automatically expanded. And all programs that use the predicate can also stay the same. All goals are automatically rewritten. And at first sight, this may seem like a quite clever use of term and goal expansion. Yes, we do pay a price, the number of facts is doubled, but on the other hand, this can vastly improve performance, because it reduces the asymptotic complexity of lookups. So one could regard this as an impressive demonstration of the power and versatility of expansion mechanisms. However, I at least don't find this very impressive, because why is all of this even necessary? It's because indexing is too weak currently. And my hope is that in the future we can simply forget this because it's no longer necessary. So I hope that indexing in Prolog systems improves. And therefore, this is maybe not a very good example either, because it only delays the work on the underlying problem. But phrased a bit more generally, I think it's still an interesting use case of goal expansion, among others. And goal expansion corresponds maybe most closely to what other languages call macros. And indeed, in the literature, goal expansion is sometimes also called macro expansion. And sometimes also term expansion is used to implement something more specific, and that is then also called macro expansion. And it's quite striking how well this fits into Prolog. It's a very simple and a very uniform mechanism, in the sense that it's exactly like all Prolog predicates, a relation between Prolog terms. So it's also really easy to use. Still, a few questions remain. For example, what is the scope of expansions? Well, we've already seen a distinction between module local and global scope for expansions in the user module. Now, the issue with this is that, for example, Prolog also uses libraries internally to implement the top level and so on. And as soon as these libraries are loaded anywhere, their expansions are also loaded. And therefore, a few expansions are always present in Prolog. That's of course not ideal. For instance, it makes it harder to develop such libraries, because the background expansion may unexpectedly interfere. So we would benefit from more control over the scope of expansions, so that the expansion is present only in applications that load these libraries. Maybe we need different levels of expansions. Or as another example of this, are meta calls subject to goal expansion? I mean a goal that is not known at compilation time, but only at runtime. Like this g here, a variable. Should this be goal expanded at runtime? Well, expansion of course slows down execution. Why should we pay this overhead for every meta call? If we are already running the program, then we can simply call the goal, and the goal can describe everything by itself, right? Or phrased differently, is a goal expansion ever worth doing at runtime? Yes, the top level is a very notable example. For instance, let's say we post a CLP-Z constraint on the top level, even a simple one like this. And we want to know how fast the library is. Then a single invocation doesn't help a lot because that's of course instantaneous. So for benchmarking, we will invoke the goal many times, say 1,000,000 times, maybe using forced backtracking like this. Now the goal is called over and over. And we can be certain that people will try this because it's really interesting. Is this slow or is it fast? Now, as I see it, the top-level interaction should reflect the performance that the same goal would have in programs. Everything else could very easily lead to a completely wrong impression. For instance, if the top level were substantially slower, then someone may incorrectly conclude that the same goal is also slow in programs and may not even try it. So let's take a look at the top-level implementation of Scryer, especially run query goal. This predicate is given a query, a goal, and it calls the goal, exactly as it is. So notably, it does not perform goal expansion. Why? Because it doesn't have to. Because in Scryer Prolog, the engine does it for us. Scryer automatically performs goal expansion for all meta calls. But not all Prolog systems do this. And in such systems, we could perform the expansion ourselves. For instance, we could simply call expand goal here to make sure that the goal is expanded. That's of course quite ad hoc, right? Because why should only top-level goals be expanded? What about other meta calls, like here in the time library? The same situation. A statically unknown goal is called. Should this also be goal expanded? And at least as I see it, the small overhead we pay for built-in goal expansion of meta calls is worth it. Because it avoids surprises and also reduces mental overhead. We don't have to worry all the time, have we thought about all cases? The engine does it reliably for us in all cases. What about partial goals? Are they goal expanded? From meta predicate directives, a Prolog system can tell which arguments are goals and partial goals. For instance, let's consider format again. We saw that goal expansion is used to transform format goals into calls of phrase to stream, which is defined in library PO. And in PO, phrase to stream has a meta predicate declaration. In this case, it states that the first argument is a partial goal, missing 2 arguments. And the same for other predicates here. And a Prolog system can take this knowledge into account. For instance, in this case, the partial goal is format underscore with 2 specified arguments. And from the meta predicate declaration, Scryer knows that 2 arguments are missing. So it knows that this indicates format underscore with 4 arguments. And the library defines a goal expansion for this predicate, namely here. This goal expansion is actually meant for the non-terminal format underscore, which is translated by term expansion to a Prolog predicate with 2 additional arguments. So this hinges on the implementation method of TCGs. That's suboptimal and there may be a way to improve this. But the key point here is that Scryer Prolog applies goal expansion also to this partial goal. For instance, let's ask for the expansion E of a goal format where the format string is known. Then we see maybe the most interesting part of the expansion. The partial goal format underscore, which we expected due to the above goal expansions, is expanded to format cells by another goal expansion. Such known format strings are compiled to a more efficient mini-language that is interpreted at runtime. And this makes format more efficient, because it no longer needs to analyze the format string at runtime. So that's a very nice feature to have. Then are expansions themselves subject to expansion? We saw that it's the case in some, but not all systems. So more control over expansions seems valuable. And also other questions, such as, are there special facilities for queries, as in Sixtus and so on? So these questions are broadly about the scope of expansions. What is expanded? How much is it expanded? And it's also a trade-off. Are we willing to sacrifice a bit of speed to achieve more consistency and fewer surprises? It seems like a good idea. Another question is the visibility of expansions, because on the one hand, we want to see whether an expansion was applied. And on the other hand, we sometimes want to see the original program without expansion, notably when using program fragments for declarative debugging. Then we want to see the original program. For instance, in the case of nut sum, what if we assert 0 plus 1 is 2? That's of course not the case. And why is it not the case? Even if we generalize away the first goal, it's still not the case. So the remaining fragment explains the failure. But in the expanded version, the remaining fragment is still quite long. And therefore, the expanded version is far less suitable as an explanation. This is a case where we want to see the original program without the expansion. The star is from library debug. And this is necessary for Gupo, library diadem, and so on. And the design question is, how do we access the original program? And one of the most important and also most interesting design questions can maybe be phrased as compositionality or maybe modularity. For instance, let's consider if underscore used with CLPZ-T as its first argument. We know from the meta predicate declaration of if underscore that's a partial goal with one missing argument. If then else. Now, it's clear that at least something here can be goal expanded, because something is known about the partial goal. In fact, quite a lot is known about it. But how exactly would we define the goal expansion we need here? This is a case where expansions of two libraries, rev and CLPZ, need to work together in a sense. What we don't want is a definition that takes such a specific combination of goals into account and therefore only covers that specific case. What we do want is generality of definitions, so that they work in many different concrete situations. Ideally, at least, an expansion is defined only for if underscore in library rev and separately only for CLPZ-T. We want a modular and general mechanism that can cover all such combinations without having to enumerate them all. And related to this, maybe the most important point of all, goal expansion must preserve all solutions and errors. In other words, using goal expansion must be semantically equivalent to not using it. That's something that the mechanism itself, of course, cannot guarantee, but we must guarantee it when writing expansions. For instance, let's take this example. This is if underscore again with a cut and 0 as goals. That's of course completely nonsensical. This goal will never occur in any sensible program, but it will occur, for example, when testing the library and when a program systematically tries everything that can arise. And if underscore must always work as intended, no matter what nonsense we throw at it and whether or not goal expansion is applied. For instance, meta-calling cut is not the same as having a literal cut in a rule. And therefore, if we expand a goal too literally, then we may accidentally change its meaning. So we must be careful when expanding goals. In this case, if we expand if underscore, then we must wrap the cuts, for instance in call. And then it's good to know on which properties can we rely. For instance, are such call wrappers automatically removed when they aren't needed? If so, then it simplifies our expansion code. Because even if we are overly cautious with the wrappers, then the underlying system will keep the code efficient. And that's good, of course, if we can rely on such properties. Now, one moment. What is going on here? We've seen that term and goal expansion, sometimes also called macros, are very powerful. And also that almost every Prolog system has an expansion mechanism, at least in some form, even if limited. We've seen, for example, that DCGs can be implemented with term expansion. Many Prolog systems use this approach. But there's no consensus between systems on how these mechanisms should work exactly. How can this be so long after the Prolog standard was published? Well, consider how these things develop. First, someone has a problem, such as how can we implement DCGs, and searches for solutions. Then term expansion is found as a mechanism that can solve this. And it's quite general and can also solve many other problems. So for a time, the mechanism works well. But as we use Prolog more and more, new problems are found. For instance, how many constraint solvers are implemented in Prolog, so that goal expansion even plays a role? Currently, only a few. Or what about format? In which Prolog systems is format even implemented in Prolog? Again, only a few, and also only very recently, since only a few years ago. Or what about library debug? Which Prolog systems even ship with this library? So far, only Scryer and Trailer. The same for if underscore and library rave. These systems are now the first where such questions even arise. Or take quads, for example. No system supports them yet. And thus, shortcomings in available expansion approaches are found over time. And at least for some of the cases we've seen, all existing approaches fall short. And therefore, the task is not to promote one of the existing approaches over others. Rather, the task is to find the best formalisms together. And I invite you to help with this. Let's not get too comfortable in a place that stunts growth. We have to be on the lookout and try to find something better. A safe haven. And when we find a candidate, we ask, do we have everything we need here? Is this an architecture where everything fits perfectly? And can we stay here?